This set of notes is about intermolecular forces. As always, there's a set of notes been provided to you in Schoology, or you may take your own. All right, if we just start by breaking down the word inter, of course, means between. There's a prefix meaning between. Molecular, having to do with molecules. So these intermolecular forces are the forces between molecules. Okay, so attractions between molecules, the good thing always to remember about them is they're not nearly as strong as the intramolecular attractions. Intramolecular attractions are the ionic bonds, the covalent bonds, and the metallic bonds that hold compounds together. But they're still really important because they are the things that if something is a molecular compound, that will hold it together at the macro level or at the human base level. So for example, in your body, right, most of the molecules that make up our body are held together by covalent bonds. It's the forces between them, the intramolecular forces between those molecules that hold structures like our body together, not the covalent bonds. So again, the covalent bonds hold the atoms within the molecule together, but the intermolecular forces hold one molecule to another molecule, with one exception, which we'll talk later on in this unit about. Okay, altogether, the intermolecular forces that we're going to be discussing today have a common name. They're also called the van der Waals forces. So if you hear someone say van der Waals forces, they mean intermolecular forces of all types. So what are those types? Okay, well, those types are come in a bunch of different varieties that we've given different names. So London dispersion forces are one major type. The other major type are dipole interactions, and we'll talk about those separately. Okay, underneath dipole interactions, we have dipole-dipole forces, dipole-ion forces, dipole-induced dipole-dipole forces, ion-induced dipole-ion forces, and hydrogen bonding. For the most part, all of these tell you exactly what's going on in the situation. And so the important thing for us to remember here again is if we're talking about a dipole, this is a polar molecule, right? Dipoles indicate polarity. All right, so we'll start with London dispersion forces. All right, London dispersion forces are probably one of the most difficult to understand, but they're not terribly complex. So London dispersion forces or dispersion forces are, or sometimes just London forces, are attractions between instantaneous dipoles and an induced dipole. What? What does that mean, Mr. Murray? Well, we know that electrons and orbitals repel each other, right? That's what Vesper theory is based on. So what happens is as they're repelling each other, occasionally what's going to happen is you'll end up with electrons or greater electron density on one side of an atom than another. Okay, at that instant, the atom is polar. So I give you an idea here. So we've got electrons zipping around over here, right? Electron density is fairly balanced, north-south, east-west on that. But as those electrons continue to move around, you might end up with a situation where, we got one atom right here, where both electrons kind of end up on one side for a moment, okay? And at that moment, you have an excess of electrons on the left side and a absence of electrons on the right side. And so for that particular moment, you end up with a partial negative charge on the left and a partial positive charge on the right. This is our instantaneous dipole. Why is it instantaneous? Because it's based on the instant that these electrons are imbalanced in that particular atom. Now, randomly, you could have the same thing happen on the other atom, and you could end up with instantaneous dipoles next to each other, and then you'd have partial positive and partial negative charge and an attraction. But it doesn't even have to happen that way. What typically happens then is these electrons that are now focused on this left side of this particular atom will repel the electrons over here on the other side. Right? They've gotten close to any spot over here, so these electrons over here will want to stay away from those electrons over there. So then at this particular moment, because the repulsion has happened, the atom next door now has also a partial negative charge on one side and a partial positive charge on the opposite. Partial positive partial negative, opposite charges attract. Right there is your London force. All right. So this idea that electrons on one side of the atom, or electrons will repel electrons in another atom, happens to varying degrees depending upon which element's atom we're particularly talking about. And the tendency of the electron cloud to distort that way, in other words, for electrons to get imbalanced in this particular way, is called polarizability. This word is going to become a very, very important word as we start talking about London forces and their strengths in a little bit. Okay? But the end result is that opposites attract and the London dispersion force occurs. Now, this happens in all molecules, whether they are polar or nonpolar, because electrons move around in all atoms and all molecules. So as a result of that, no matter what atoms or molecules we have, there's going to be some electron imbalance at different times, and as a result of that, you get London dispersion forces forming and unforming all the time as these electrons move around to different locations. All right, now just a second ago I said that this idea of polarizability, the ability of a particular atom's electron cloud to become imbalanced, is very important in this, okay? And so if we think about factors affecting London forces, that idea is the very first one. The more polarizable something is, the greater the strength of the the London force. Okay, so you can imagine it being this way. If my electron cloud is easier to distort so that electrons end up imbalanced on one side or another, I'm going to have more of these interactions between partial positive and partial negative, and so therefore the London force will be stronger. Okay, so what creates greater polarizability? Well, first of all, the more electrons an atom has, the more polarizable it is. All right, so that means that if you got larger atomic or molecular size, it's more polarizable. Why is that? Well, we know that if we have more electrons, that means that there's more electrons further away from the nucleus. That's going to give them more freedom to be pushed around. They're not as controlled by the positive charge in the nucleus. All right, so bigger atoms in terms of ionic radius are more polarizable. Okay, it goes right along with that high atomic or molecular weight will also make you more polarizable. Okay, and the reason for that again is if I'm got more molecular weight, more atomic weight, I have more electrons, period, right? Bigger atoms, weight-wise, more electrons, more mass, more electrons. The other thing that will create greater polarizability is if a molecule has more pi bonds. Those are more polarizable as well, because remember, those pi bonds, the electrons run north and south. They tend to be less localized. And so as a result of, have to be less localized. And so as a result of that, they can move around. They're less controlled by the attraction forces as well. And so you end up with, if you've got a molecule has more pi bonds, it is also more polarizable. And you'll end up with stronger London forces. Okay. The last couple things that affect London forces are greater surface area contact. Okay. So if we have a situation where you have atoms from adjacent molecules that can get closer to each other and you get more of them to do that, that means you're going to have more London forces happening between molecules, and you end up with a greater net force because all of those little London forces will add up with one another. So as a result of that, long, skinny molecules tend to have more contact area, so they have greater net intermolecular force. Things that are balls or have lots of branches off of them are going to have less contact area. All right, and so that ends up with giving us less net force. Okay, so that's these diagrams over here show us that, right? Every single one of these atoms can interact with one another in terms of London force, whereas neopentane, which has the exact same formula as pentane, you only get these ones interacting, right, between those two molecules. So as a result of that, you end up with a greater net London force or intermolecular forces in the pentane than you do in neopentane, just because there's greater contact. Same thing would happen in branched hydrocarbons. So if I have something like this, and then it's got a side branch that comes along, well, that side branch is going to prevent somebody else from getting close to this molecule. And so as a result of that, again, balls and branches cause you to have less London force between two molecules. Okay. This graph right here, trying to show us a little bit of that stuff that we've talked about at the beginning here, which is just simply larger atoms and more weight make you more polarizable. This data is showing this. So as I go down the group for the noble gases, or go down the group for the halogens, I get bigger and bigger atoms in terms of both radius and in terms of number of electrons. And so you end up with greater London forces between the atoms of those, or molecules of those substances, or atoms of those substances. You'll notice that in this particular place, boiling point is being used to measure those intermolecular forces, and that's because boiling point is a proxy for intermolecular strength. If you think about the other day, in order to turn something into a gas, you have to break the connections between the molecules so that they can move around freely. Well, what are those things that you're breaking apart? The IMF. So again, boiling point can be a stand-in for figuring out how strong the net IMFs are between two different substances. Okay. So that's London forces. All the rest of the IMFs are all dipole interactions, and they're called dipole interactions because they all involve a polar molecule of some way, shape, or form. All right. So these are particles that have permanent charges. Okay. They might be partial charges, partial positive, partial negative, because of the polar molecule, but because of those partial charges, they have permanent attractions to the other molecules and charged particles. All right, so what kinds of things are involved in this? Well, if you have a polar molecule and another polar molecule, we call that a dipole-dipole. If you have a polar molecule and an ion, ions have charges, you end up with a dipole-ion in molecule. You can also have a dipole-induced dipole-dipole. This would be between a polar molecule and a non-polar molecule, because the polar molecule creates a temporary dipole in the other one. Crazy stuff. Ion-induced dipole-ion, same deal. The ion induces a dipole. And the last one that we have is called hydrogen bonding, which is just a particularly strong dipole-dipole force. We're going to go through all of these one by one, but right now I'd like you just to take a moment, look at all of these diagrams that are over here on the right, and look at them and see what can you figure out about these different dipole interactions just by looking at the molecules that are, or the diagrams that are shown here. After you've taken a few minutes to look at each one and try to figure out what it is, come back and we'll go through them all. Pause the video now and take a moment or two to look. All right, so let's go through them one at a time. Dipole-dipole forces, okay? Dipole-dipole forces are molecules with permanent dipoles, or two polar molecules attracting each other. The positive end of one is attracted to the negative end of the other. All right. These are only important at close distances. So basically, dipole forces act from one molecule to the molecule right next to it, not across multiple molecules. All right. So here is CH3CN. Okay. One side of this molecule, the nitrogen side, is partially negative. The other side, which has the carbons and hydrogens, are going to be partially positive, and that's likely because we have a lone pair of electrons up here. But that just means that the nitrogen of one atom, or of one molecule, is going to be attracted to the hydrogen of the other molecule. Okay, these forces form throughout, positive attracting to negative, and you end up with dipole-dipole forces. Okay. dipole-dipole interactions get stronger and weaker based on the polarity of the molecules. So the more polar the molecules, the stronger the dipole-dipole force, because again, that just means that the partial positive and partial negative ends of them are stronger when you're more polar, and they're weaker when you're less polar. Okay, so here we've got propane, not polar. No, dipole-dipole interactions are weak there again, because all we're going to have is London forces. But as we move in this direction towards more polarity, you end up with stronger dipole-dipole forces. Right. Second kind of dipole interaction is an ion dipole force, which again is exactly what it describes. It's an ion with a polar molecule. So the positive end of the dipole attracts to negative ions. The negative end of the dipole attracts to positive ions. The greater charge on the ion and the greater polarity in the dipole increases strength, because again, we are increasing the amount of charge. So by Coulomb's law, you have stronger attractions. These are responsible for ionic substances' ability to dissolve in polar solvents. So for example, we know that table salt will dissolve in water. Okay, water is a polar molecule. Table salt is an ionic compound. And so as a result of that, you can end up with these ion dipole forces between the hydrogen end of the water and the negative chlorine, and the oxygen end of the water and the positive sodium. Okay, and that's because the oxygen end of a water is partially negative and the hydrogen end is partially positive. These are ion dipole forces between those substances. Third kind of dipole interaction is a dipole-induced dipole force. This is going to happen between a dipole and a nonpolar molecule. So essentially what's going to happen here is, here's acetone. The oxygen end is partially negative. The opposite end is partially positive. Well, when acetone comes next to a molecule that is nonpolar, what's going to happen here? Well, this is a negative end. So the electrons that are within this molecule on the right are all going to shift away from it within their particular atoms. Okay, and so again, at that particular moment, you're going to end up with an induced dipole on this side that is partially positive on the left and partially negative on the right. Okay, so that's your dipole-induced dipole-dipole force. Okay, the thing about this is, again, this is going to change a little bit as these molecules move around. These will be a little more temporary. They'll come and go. Okay, but the force of these is dependent upon two things. First of all, the more polar this molecule, the stronger the force is going to be. And on the nonpolar molecule, it goes back to that idea of polarizability. So the more polarizable these particular elements within here, atoms within here are, the stronger the dipole-induced dipole-dipole force is going to be. Similarly, we have ion-induced ion dipole forces. I don't know, this picture is the wrong picture. So let me just get rid of this for a second, and let's go ahead and we'll put in a negative ion like chlorine. Okay, so same thing's going to happen here, right? The chlorine is going to go ahead and repel electrons in that direction, making this partially positive on one side and partially negative on the other side. So if we had a sodium over here, it would attract to this side, chlorine would attract to that side. Okay, what causes the force of these to increase? Again, the greater the charge on the ion, Coulomb's law, as well as the greater the polarizability of the atoms within the molecule. So all of this comes together to create some trends. And we'll take a look at these trends one by one. You'll notice that the orange one here, it runs a little bit different than the other ones. They kind of all follow, the other three all follow the same shape. So let's look at this for a second. So this is going down the group that starts with group that starts with carbon at the top as they combine with hydrogen. Okay. What's going to be interesting about these is these are all going to be non-polar bonds. They're also non-polar molecules because they're all tetrahedral and symmetrical. So as I go down the group from carbon to silicon to germanium to tin, you'll see that the boiling point, again, that's our proxy for IMFs, increases. Well, why is that? Well, again, if these are all nonpolar molecules, the only forces that are going to be involved in them, intermolecular forces, are going to be our London forces. What do London forces depend upon? They depend upon polarizability. What does polarizability depend upon? It depends upon number of electrons. Okay, number of electrons, there are more electrons in bigger molecules than there are in smaller molecules, and so as a result of that, or bigger atoms than smaller atoms, so carbon is the smallest. As we go down the group, the atoms get bigger, and so you get more polarizable, and so you get a higher, stronger London forces and a higher boiling point. Okay. Same thing occurs in our other groups. Okay, the halogen group, the group that starts with nitrogen, the group that starts with oxygen. Right. As we go down them, right down here to the biggest atoms, London dispersion forces are dominating here, and so you see the boiling point going up. However, there's a dramatic spike back here at the beginning for the smallest molecules in each group. And the reason for this has to do with the fact that oxygen, fluorine, and nitrogen are three of the most electronegative atoms on the entire chart. And so as a result of that, each of these molecules ends up being very, very polar. And because they end up being very, very polar, the dipole forces within them dominate and are really, really strong. All right. So in those three cases where we have a hydrogen bonded to nitrogen, oxygen, or fluorine, we give those dipole forces a special name. We call it hydrogen bonding. Okay, so these occur between the hydrogen end of a molecule that has a hydrogen bonded to a nitrogen, oxygen, or fluorine, and the negative nitrogen, oxygen, or fluorine end of the other molecule. Okay, they are the strongest dipole forces due to the high electronegativity of nitrogen, oxygen, and fluorine. They are the most polar dipoles, so they have the strongest dipole forces. These forces, hydrogen bonds, are very important on small molecules. All right, so again, how does this work? Well, you can see here's water and ammonia, right? The hydrogen attached to nitrogen and the oxygen on the next molecule, those are places where we can see this. Okay, same thing, you can see it with all of our other structures here. Okay, it's always the hydrogen on one attracted to the oxygen, nitrogen, or fluorine on the other. All right, so when we take all of these together and we try to figure out what is the net effect of our different van der Waals or intermolecular forces, we sometimes will ask ourselves, what has the greater effect? Are dipole interactions more important, or are London dispersion forces more important? Okay, well, it depends, right? So if two molecules have about the same amount of size and their shape are similar, so we're talking about long chain molecule and another long chain molecule, or two small ball-shaped molecules. If they're comparable size and comparable shape, then what's really important between them is the dipole forces that occur. Okay? If one molecule is much larger than another, for example, their molar masses are 75 grams different, or their molar atomic weights are 75 AMUs different, then dispersion forces are what are most important in terms of determining which has stronger intermolecular forces. Okay? If one molecule has greater surface contact than another, so again, a long chain molecule versus one that's super branched, dispersion forces, again, are going to be the one that most likely determines which one has stronger IMFs. Okay. Last piece is that IMFs are additive. Okay, so for example, if all other things are equal and you have two hydrogen bonds in one kind of molecule and only one hydrogen bond in another kind of molecule, then the one with two hydrogen bonds per molecule is going to have stronger IMFs than the one with one hydrogen bond per molecule. Okay. All right, that is your primer on intermolecular forces. A lot of information there. We will work on these in subsequent classes to help you build understanding, but at this point, being able to identify the different kinds of London dispersion forces and in general understanding what makes them stronger or weaker, each of them, and understanding how to compare the intermolecular forces between two different substances to try to figure out which one's stronger or weaker based on these rules is what's important at this point. So we'll work on this. Thanks for watching. Have a good day.